Hi everyone, this is video 9, and today I'll be talking about what's, in my opinion, one of the most important topics in computer science, recursion. So what is recursion? Well, recursion, at the end of the day, is the process of solving a problem by progressively reducing it to easier versions of itself, and then once you have easier versions of the problems, you can solve those easy versions to get and put that all together to solve the larger problem. And a recursive function specifically is a function that calls itself either indirectly or directly. So that's pretty abstract, so let's go through an example. And I think this is an example that we can all relate to. You're sitting in the back of a large lecture hall or some auditorium, and you need to somehow figure out the row that you're in. Which of the following do you do? Do you count the rows from the front, or do you ask the person in front of you what row they are in, and then easily figure it out from that? So yeah, these are two viable methods to solve this problem. And what I'm going to show you is that these two methods correspond to iteration and recursion. Counting the rows from the start is what we do when we do iteration, and determining the row from the person in front of you is recursion. And how that works is the person in front of you knows what, let's say he knows what his row is. Well, then you immediately know what your row is, because you solved this, the person in front of him solved a simpler problem. But also, let's say the person in front of you didn't know what row he is. What does he do? He asks the person in front of him, and so on and so forth until you get to the bottom, and then you can build yourself back up by the person telling the person behind him what row he is, and then the person behind him figuring it out from there, and the chain goes on until you figure out what your row. And if all works out, that gives you a right answer. By the way, this picture that I have here is actually one of my friends from Berkeley. This is a complete side note, and he won the recursive art contest in 61A. So this is some of the cool things you can do with recursion. So this is very cool stuff. Now, let's look at this count rows example. So I'm not going to actually code this because this is a pretty voodoo function, because at the end of the day what we could have done is we could have just returned n, because n is the row that you're in and you're trying to figure out n. But let's say we couldn't do that shortcut and we wanted to figure out, well, you could start, the iterative method is, as we know, you start at 0 and then you go all the way up to n, not including n, and then you increment and then you get your count. So that's like counting the rows from the start. Now recursively what we do is we ask the person in front of us. So what is that? So asking the person in front of us is symbolically represented by this call to itself. Count recursively on the n-1 person. Because the person in front of you, we know, is in a row that's 1 less than us. And then each time we do that, we know we add 1. Because once we get that, we know we have to add 1 to get our actual row number. And of course, if you're in the front, you just return 0. So this is, we're assuming that the front is 0. It really doesn't matter if we did 1 or, that's a little trivial, so don't worry too much about that. So that's a pretty simple example of recursion. Let's look at a little more complex one. We're going to look back at one of our favorite functions, factorial. And what we did initially when we defined factorial is we defined it iteratively. What is factorial? Well, hey, it's just 1 times 2 times 3 all the way up to n. And this is represented by this mathematically. And as a function, it was represented as such. And this is an iterative definition of factorial. So now we have to ask ourselves, how can we define factorial recursively? And we can. So we know 0 factorial is 1. That's given. And we know 1 factorial is also 1. Now 2 factorial, we notice, is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And n factorial is just n times n-1 times n-2 all the way up down to n. So you might be wondering, why am I doing this? This is just like the backwards of this, right? Well, because I did it like this, we can notice an interesting pattern. Notice that when we do 2 factorial, it's 2 times 1. And 1 is just the result of 1 factorial. When we do 3 factorial, it's 3 times 2 times 1. 2 times 1 is the result of 2 factorial. And so on and so forth. So really, n factorial is just really n times n-1 factorial. So you guys might have already known this, but from doing some mathematical manipulations with factorials, this definition of factorial is very useful when you want to cancel things out. So you might, but this is why it's true. And also, this is kind of a little subtle, but 1 factorial is just 1 times 0 factorial in reality. So now we have a recursive definition of this. N factorial is 1 if n is 0, and otherwise it's n times n minus 1 factorial. And this leads to a very easy definition in terms of code. So let's do that right now. So I'm going to define factorial recursively. And what I'm going to do is I'm just going to quickly write some doc tests. Factorial recursive on 1 should give us 1. Factorial recursive on 3 should give us 6. And then factorial recursive on 8 should give us 40,320. And what we're going to do is, well, let's copy the logic that we had. If n is 0, we return 1. Otherwise, we return n times n minus 1 factorial. If n is equal to 0, we return 1. Otherwise, we return n times n minus 1 factorial. Well, what's factorial? What's n minus 1 factorial? It's just, that's just figured out by calling factorial recursively on n minus 1. So this can be thought of as an abstraction for factorial. Alright, so now let's test this. Okay, let me quickly go into my documents, the correct directory, sorry. So, and then what we can do is we just run the doc test. Doc test. And it works. So now let's look at this a little more deeply. Every single recursive function at the end of the day has a particular anatomy in that it's always made up of one or more base cases, and then there's a recursive case. So in this factorial function, our base case is our n is equal to 0, and our recursive case is the else statement. Now, how do we figure out what the base case is and the recursive case is? Well, usually the way I like to solve recursive problems is I always like to think about the base case because it's really the simplest instance of the problem. So in terms of factorial, what's the simplest factorial we can take? 0 factorial. So there's our base case, and we return 1. And then now the recursive case is sometimes tricky because you have to figure out how can we solve larger versions of the problem in terms of smaller versions of the problem. And this is the best way to figure this out is honestly write this entire pattern out and find this natural recursive definition. So one thing we notice in the recursive definition of factorial is that we can calculate the factorial of any number if we know the factorial of the n minus 1th number. And because of this, we can compute factorial as such. And that gives our natural recursive definition.